Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 12-4 lesson on inverse matrices. This will be another two-parter. In this one, in part 1, we will be finding inverses of matrices, and we'll also be using that to help solve matrix equations. In part 2, we are going to use inverses to solve systems of equations. In order to understand the concept of an inverse, we actually need to first start with the concept of an identity, because these two are linked quite a bit. So the idea of an identity, just without even thinking about matrices, you might remember when you were first learning about the identity property, there was the additive identity, 0, which didn't change anything when you added it to a number, and there was the multiplicative identity, 1, that didn't change a number when you multiplied by that. Well, matrices have basically the same kind of idea with multiplication. So the identity matrix, which we often refer to as capital I, is a matrix that does not change the value of other matrices when multiplied by those. So you could think of this as kind of the matrix version of 1. So just to write this out as sort of a little equation, if we have some matrix A and the identity matrix for that I, A times I is just going to be A. It's just going to give you whatever the non-identity matrix was. So what would this identity matrix actually look like? What would it have to basically accomplish nothing? So the identity matrix is going to contain a diagonal of 1s going down and to the right, and it's going to be 0s everywhere else. And there's an identity matrix for every square size of matrix. So for example, here's the 2 by 2 identity matrix. We've got this diagonal of 1s and 0s in the other two spots. And there's a 3 by 3 identity matrix. We've got 1s going this way and 0s everywhere else. And there's a 4 by 4 and 5 by 5 following this same kind of pattern. Now, if you don't believe me that this is actually the identity matrix, just kind of the intuition here, when we do our matrix multiplication and we multiply each row by a column, the 1s in these identity matrices are going to preserve one of the things that we're multiplying by, and the 0s are going to get rid of everything else. So the dual action of the 1s and 0s gives us what we started with. Or if you really want some proof, let's go to the Desmos calculator. So just for fun, I'm going to create a 3 by 3 matrix, and then I'll multiply it by this identity matrix here. So let me do new matrix, 3 by 3, and I'm just going to randomly put in some numbers, whatever. They need to be numbers though. Let's see, 1, 5, 7, let's do -2, 3, and -4, whatever. And now let me make a new matrix, and we'll call it B, but it's really the identity matrix. So again, this is just going to have 1, 0, 0, 0, 1, 0, 0, 0, 1, and there's our identity matrix. And let me just go back up here and make sure that's actually a number. Let's make it 0. So going down to this line here, if I multiply these together, I'm maintaining that I'm going to get just matrix A. Let's see if this actually works. So A times B is just A. And in case you thought this was a typo, if I just have B, it gives me the identity. Now what if I do B times A? Then we get matrix A again. So it actually doesn't matter which way you multiply by the identity matrix, you still get what you started with. Okay, so we have this idea of an identity matrix. I guess the follow-up question is, who cares? Like, what use is a matrix that literally changes nothing when you multiply it by something else? So by itself, it's not much good, but the idea is that if you can turn another matrix into the identity matrix, you basically are canceling out that other matrix if it's being multiplied by something. Like if you have the equation, let's just say a simple one, 3x equals 6. This equation here. Now, if I wanted to solve this equation for x, a lot of us think, okay, I just have to divide by 3 and we're good. Well, what's really happening is when you divide by 3, you're multiplying by the multiplicative inverse of 3, which is 1/3, and you're turning this 3 into a 1, and 1x is just x. So our whole concept of canceling things out to solve basically means turning those things we're canceling into the identities. So although the identity by itself isn't much use, if you can turn something into this, we could use this to help solve some matrix equations. So let's dig into the idea of what we would need to use to turn something into the identity. The thing we need to use to turn something into the identity is called the inverse. So the inverse matrix, which we note with a little -1 next to the matrix name, turns another matrix into the identity when you multiply the original matrix by this inverse matrix. So as an equation, we can say A inverse times A, and also A times A inverse. The direction actually doesn't matter. Both of those give us the identity matrix. So that's cool, but how do we find the identity matrix? So there's a convenient formula for a 2 by 2 matrix. So I'll give you the inverse formula. There is a process you can follow for a matrix of any size as long as it's a square matrix. That's a condition, but it is quite a process. The basic idea is you have to write the original matrix with the identity matrix next to it, and then do a whole bunch of row operations, so multiply rows by a number, add rows together, whole bunch of stuff until you've turned the original matrix into the identity, and then the identity will have transformed into your inverse. It's a process. Anything bigger than a 2 by 2 for this lesson, we're going to do on a matrix calculator. But here's a 2 by 2 formula that'll do at least all of that work for you with a 2 by 2. So if you're given the original matrix, which we'll say has elements A, B, C, and D, the inverse of this is going to be 1 over AD minus CB times, and instead of A and D here, we're going to switch them, so dA, and then we'll also have a -B and a -C. So this is a formula you could memorize. You could also memorize the process, which is what we do with a lot of our matrix formulas. The process here is, do you recognize what's down here? This is basically the determinant down here. We did AD minus CB. So we're doing 1 over the determinant of the thing you're trying to get the inverse for. A and D essentially switch spots. And then B and C, they stay where they are, but they are both going to be negated. So 1 over the determinant, switch A and D, negate B and C, and that'll get you your 2 by 2 inverse every time. Except for there's one situation where it won't. Because we're dividing by this determinant, if the determinant happens to be 0, that means this thing comes up undefined and the matrix actually has no inverse. So yes, it's true, there are matrices that do not have inverses. So after that long introduction of what the inverse is, why we care, and how to find it, let's do some examples with just 2 by 2s. Pause the video and try to find the inverse of this matrix if possible. Alright, so I typically do write out the formula every time I use it, just to kind of remind myself of what I need to do. So again, we need the 1 over the determinant. So that's going to be 1 over, and in this case we're going to have 20 minus 21. And now for the matrix itself, we're switching A and D. So we have a 5 in the upper left and a 4 in the bottom right. And then we're negating B and C, so -7 and -3. Next up, we need to simplify this determinant and then just multiply whatever we get through here as a scalar. So this is just 1 over -1. So we just really have -1 times this whole matrix. So distributing that, we end up with -5, +7, +3, and -4. Now, is this really the inverse? We could verify it by multiplying the original by this and seeing that we get the identity. In fact, let's do that just real quick on the calculator. So let me make a matrix for the original, 4, 7, 3, and 5, and a matrix for what I'm claiming is the inverse, -5, 7, 3, and -4. And if we just multiply those together, we should get our identity. So A times B gives us 1, 0, 0, 1, and if I switch the direction, I still get the identity. So yeah, this does work. Here's another example for you to try. Pause the video and give this one a shot. All right, so same formula as before, 1 over AD minus CB and all the rest of this stuff. So we've got, in this case, 1 over 10 minus 12. And then we've got the 2 and the 5 switching. And we have a negative 3 and a negative 4. So this is going to be 1 over negative 2, negative 1/2. So that's a little bit different than before. Multiplying this through, this is going to become negative 1. This will be 3 over 2. This will be negative, or positive 2 rather, and this will be negative 5/2. So sometimes these inverses can get a little bit ugly when these fractions are involved, but they still work. All right, let's do one more example with these 2 by 2 inverses. Pause the video, try this one out. All right, so here's our formula again. We've got 1 over, in this case, we've got negative 6 times negative 3 is 18, and 2 times 9 is 18, so 18 minus 18. Now, before we go about rearranging everything here and negating it, 18 minus 18 is 0. This is undefined. Since our determinant down here is 0, that again is going to tell us that we have no inverse for this particular matrix. And in fact, if you really want to force the issue and look up the inverse on Desmos, well, let's do that. So let me create the original matrix, negative 6, 9, 2, negative 3, and now let me just do A and then do the little negative 1 for inverse, and it's saying that we have an issue here. Singular matrices do not have an inverse. Singular basically means determinant of 0. So now that we've got a little bit of practice with finding inverses kind of as an end in itself, we're actually going to use it for something. Namely, we're going to solve a matrix equation. So we've got one matrix times this x, which is another matrix, and that equals some other matrix. So for something in AX equals B form, which is what I'm calling this, we have A, we've got X, we've got B. To solve this, we basically need to undo this A matrix, and then whatever X equals is going to be our answer. So to do that, we're going to need to multiply A by the inverse of A inverse, with the little negative 1. So we're going to find and multiply each side by A inverse. So that means you have to find the inverse first, then multiply by it. Now, when you're doing this on the left side, the order that we multiply in is not going to matter. It will make a difference on the right side, however, because the right side you're not multiplying a matrix times its own inverse. So the order is important. So when you're doing this, you have to make sure you're doing A inverse times B, not B times A inverse. Those will give you different answers. So make sure that your inverse matrix is to the left of your B matrix on the right side. So with all of that in mind, pause the video and let's see if you can make this happen. All right, so let's find the inverse first. So the inverse of our A matrix here, again, we've got our formula. 1 over AD minus CB, so that's going to be 1 over 8 minus 7. And then we're going to switch the A and the D, so we've got a 4 and a 2. And then negate the 7 and the 1, so those are both negative. Simplifying this a little bit here, this is just 1 over 1, so that doesn't really change anything. And we just end up with all the things that are inside this matrix. So this is our inverse matrix. This is our A inverse. We're going to multiply that now by hand by the left and the right side. So we have all this stuff on the left side, and we've also got all this stuff on the right side. Again, we're writing this to the left of our B matrix. So on the left side, if we multiply this out, it should give us the identity, but let's just double check. So we have each row times a column here, just to review our little matrix multiplication. So we've got 4 times 2 is 8, negative 7 times 1 is negative 7, 8 and negative 7 is going to give us 1. Now we do 4 and negative 7 times the second column, so 4 times 7 is 28, negative 7 times 4 is negative 28, that adds up to 0. Now we'll do the bottom row times both columns. So we have -1 times 2 is -2. 2 times 1 is 2. Those add up to 0. And finally, -1 times 7 is -7. 2 times 4 is 8, and those add up to 1. So we do indeed get the identity matrix. We've also got that x hanging around. And what do we have on the right side? So 4 times 2 is 8. -7 times 1 is -7. 4 and -7 again gives us 1. And now we've got 4 times 8 is 32. -7 times 5 is -35. So that's going to add up to -3. Now we do the bottom row times each column. -1 times 2 is -2. 2 times 1 is 2. That adds up to 0. And then finally, -1 times 8 is -8. 2 times 5 is 10. So -8 and 10 gives us 2. Now the whole idea here is that this identity matrix we've seen and verified when you multiply it by another matrix does not change the value. So identity matrix times x is really just x. That was kind of the whole point of doing this inverse dance. So then we can just write x equals this matrix that we have over here. So this is the end of part 1 of our lesson on inverse matrices. In part 2, we're going to use this matrix solving sort of process we've done to solve some systems of equations, and we're going to go up from a 2 by 2 to finding a 3 by 3 inverse of a matrix, so stay tuned for that. Welcome back. You're joining us for part 2 of this lesson on inverse matrices. In this part, we're going to use inverse matrices to solve linear systems. We're going to start with a 2 by 2, get some techniques, and then we'll up our level to a 3 by 3 by the end of this one. All right, so the idea with solving a linear system, we're going to build on the idea of solving a matrix equation. We're actually just going to set up and solve an ax equals b type of equation like we did in the last example. Now let's spell out what a, x, and b are in this situation. So A is going to be a coefficient matrix. It's going to have these coefficients in it. B is going to have the constants here in it. So you're going to have an A and a B matrix that actually have stuff in them. And then X is going to be your solutions matrix, which when we get to the end of the problem and actually solve for X, it's going to end up in X over Y form, which will allow you to pick out the point that's the answer for this thing. So with all that in mind, see if you can set up a matrix equation with this system and then solve it. All right, so let's set it up here. We've got our coefficient matrix, the A matrix. That's going to be a 2, 5, 1, and a 3. X is just going to be X for now, and we're going to have our constants matrix over on the right side, so 3 and 2. And now, just like we did on the last problem, to solve one of these matrix equations, we just have to find the inverse of the this term here and multiply that by both sides. So my inverse for this one is going to be 1 over, and now we're going to have 6 minus 5, which turns out to be 1. Then we are going to have, let's see, the 2 and the 3 are switching, so 3 and 2. And then we have a -5 and a -1. So we're just multiplying both sides of this by 3, -5, -1, and 2. So we do that on the left side and on the right side. On the left side, we know that this is the inverse, so we'll just get the identity, and this essentially cancels out this left side matrix, so we just end up with X. On the right side, let's multiply this out to see what our answer is. So we've got 3 times 3 plus -5 times 2. That's going to be 9 minus 10, so -1 for that top value. And then we've got -1 times 3, that's -3. 2 times 2 is 1. -3 and, or 2 times 2 is 4. -3 and 4 adds up to +1. So there we go. So then our answer, just putting it in point form, would be -1, 1. And if we want to double check to make sure that works, 2 times -1 is 2, plus 5 times 1 is going to be 3. Yep. And then -1 plus 3 times 1 also equals 2. Before we can solve a system of equations that's any bigger than a 2 by 2, we're going to need to figure out how to find the inverse of a matrix that's bigger than a 2 by 2. 2 by 2 matrices, we've got that nice little inverse formula. I mean, maybe not nice, but it's at least a formula. There isn't really any such formula for a 3 by 3 or anything bigger. So there's a process that you can follow. There's actually a few different processes, but for our purposes, we're just going to see how to do this on the calculator. This is quickly becoming one of those things that it's just easier to do on the calculator so we can do higher level stuff. So to do this on a calculator, you just need to create your A matrix or whatever your matrix is in Desmos, and then just literally type A and then exponent -1. And that will immediately give you your inverse. Now it's asking us here to use technology to find the inverse and verify the result. How do we verify an inverse? Well, we know that something is the inverse if when we multiply it both ways by the original, we get the identity matrix. So to verify, just make sure that A times A inverse and A inverse times A, check both ways, both yield the identity matrix. That's with the ones and the zeros. So pause the video and give this a shot. All right, let's go to the matrix calculator. So let me do new matrix, make it a 3 by 3, and just put all those numbers in. So 2, 1, -2, -1, -1, 2, -3, -1, and 3. There we go. And then we're just going to go down here and literally type A, and then that gives us the original, and then exponent -1. There's also a little -1 button you can press there if you like. So this is our inverse matrix, supposedly. So we've got 1, 1, 0, 3, 0, 2, and 2, 1, 1, all of that stuff. Now to verify that this is the true inverse, we're going to go back here and we'll just do a new entry. We're going to do A times A inverse, and we see that multiplying those together gives us the identity matrix. And if we just switch the position of these, and I do A inverse first, we still get the identity matrix. So just as a verification, A times A inverse times A, both equal all of this, so we are good. So now for this example, now that we know how to find an inverse, at least on the calculator, of a 3 by 3 matrix, we're going to use that with our systems of equations kind of process that we used on a 2 by 2 to solve this thing. So to solve this linear system, we're basically just going to set up and solve an AX equals B type of equation. The main difference is that that A inverse that we have to multiply both sides by, we're going to use Desmos to find that. So it's going to be a much faster process. So pause the video, see if you can set this up and find the solution to this 3 by 3 system. All right, so let's first come up with our A matrix with our coefficients. So we're going to have 1, -1, -3, 5, 2, 1, and finally, be careful here, -3, -1, and we need a 0 for the missing z that was in there. So placeholder zeros will be needed for this. For our B matrix that has our constants, that's going to be the 2, the -17, and the 8. So we've got our equation, AX equals B, and again we're doing A inverse times both sides of this. On the left side, that's just going to cancel out A and give us X. On the right side, A inverse times B is going to give us the answer. So at this point, we actually need to enter this into Desmos and calculate it. So to do this on Desmos, I'll need to set up two matrices. First one is our 3 by 3 A matrix. So 1, -1, -3, 5, 2, 1, -3, -1, and 0. And our next matrix is going to be this B matrix. Now this one has 3 rows, but only 1 column. So we've got 2, -17, and 8. And now we're just going to multiply A inverse times B like we wrote down here. So A, exponent -1, come back down and write B, and abracadabra, there is our solution matrix, 9, negative 9, 19, and negative 10. And written as a point, this is going to be negative 9, comma 19, comma negative 10. And if you want, you could quickly verify that this works. We'll just plug it in the first equation to be sure. So we have negative 9 minus 19 is negative 28. And then negative 3 times negative 10 would be 30. Negative 28 plus 30 gives us 2. So it at least works for the first one, and you can verify the other ones. So needless to say, solving with inverses and a matrix calculator is a very powerful technique. It is actually the most efficient way to solve a system of any size. So we're going to have a little bit more fun with that in a real-life context. So we have a company selling 3 sizes of fruit baskets, as shown down here. We want to know the cost of each type of fruit. So we've got our small basket, it's $5.99. We've got 2 apples, 2 grapefruits, and a peach. The medium basket's got 3 apples, 2 grapefruits, and 3 peaches, and has a different price, and so on and so forth for our large basket. So set up a system of equations for this, and then use your inverse matrices to see if you can solve that. Pause the video and give it a go. All right, so for our first equation, we're going to let, for all these equations, I'm going to let A represent apples, G is grapefruits, and P is peaches, at least the prices of those things. So for our first equation, we can write 2A plus 2G plus 1P equals 5.99, 5.99. For the next equation, we've got 3A plus 2G plus 3P equals 9.27. And then finally for our large basket, 5A plus 3G plus 4P equals 13.76. So these numbers would be kind of nasty to work with if we were not using a calculator, but we are. So let's set up our A matrix. That's our coefficients. So we've got 2, 2, and 1, 3, 2, 3, and 5, 3, and 4. So those are pretty innocuous looking. For the B matrix, though, we've got these crazy decimals, 5.99, 9.27, and 13.76. Just like before, we set up the equation AX equals B and multiply both sides by A inverse. And now let's go to Desmos to put all this in. So let me do my A matrix. Again, that'll be a 3 by 3 for this problem. So 2, 2, 1, 3, 2, 3, and 5, 3, 4. And then let me do my B matrix, 3 rows, 1 column, 5.99, 9.27, and 13.76. Now let's do A inverse times B, and that comes out to 0.9, 1.5, and 1.19. So 0.9, 1.5, 1.19, great. So what this actually means for the real life context here is that A, that was our first one here, apples, that's 90 cents. Let's see, grapefruits are going to be $1.50, and then our peaches will be $1.19. And with that, we have reached the end. Congratulations on making it, not just through part 2, not just through inverse matrices or matrices in general, but through all of Algebra 2. It's been a long journey, lots of challenges, but I'll tell you, I wouldn't undo a thing. Mr. Sutton, signing off.